That's to the talk of Professor Andrei Klimov from the University of Guadalajara, Mexico. The talk is entitled Semiclassics, discretizations and long-time approximations to the quantum dynamics.
Buenas tardes. Buenas tardes. Buenas tardes. First of all, I feel that is not only my honor, but it is my duty to be here in this celebration because maybe not everybody knows, but Viktor Vasilievich was my PhD advisor. So I owe him so much and appreciate not only his wisdom, but his patience and his kindness, which is not very common in scientific environment, I suppose. I wasn't very accurate student, so he spent a lot of time chasing errata and correcting my equations. I remember this very well. So thank you very much, and this is a great pleasure to be here. So my talk is here, and the purpose of this talk is not to expose a bunch of new results, but rather discuss some methods which may be not very common or not very commonly used to improve something we people call semi-classical approximation, which is known as always as truncated Wigner approximation. Maybe some of you guys worked in this with this kind of approximations. I understand that everybody from different fields, so it is not easy to understand what is going on. I will try to be more compact and explicative, but if not, please ask me questions during the presentation. Probably this would help a bit. So, semi-classical approximation, when we talk about semi-classics, what we really mean, we think that we can and we want to describe some features of quantum evolution using information about dynamics of the corresponding classical system. What kind of information? Basically, trajectories, nothing else we have in classical system. And this subject was studied many, many years ago, and it is not really to do this. Why? Because usually in the Hamiltonian we work with, the expansion parameter, which in this case would be the inverse effective size of a system. So this expansion parameter is normally not present in Hamiltonian. Then it is not clear from the beginning what to do. Many people call semi-classical approximation, and we saw today two talks when they just have Heisenberg equations, and instead of operators, they put functions and solve these equations. Usually such an approximation has nothing to do with real dynamics, or it maybe for some very specific states, it gives some coincidence with the exact dynamics, but for very, very, very short time. So when we talk about quantum chaos considered from this point of view, you just don't believe, because if you do exact numerics, which requires, of course, a big computer, as Barry said, a good student, you get a completely different result. So what we want to develop a sort of perturbation theory where the small parameter is, as I told before, the inverse effective dimension of representation, the effective size of a system. And develop such perturbation theory is not very clear how to do. And apparently, the most natural way to do this is going to the phase space representation. So phase space formulation basically consists in what? In mapping operators into distribution in phase space. Such a map can be simple, can be not very simple. This depends very much on the symmetry of our system. If the symmetry is simple, say harmonic oscillator, spin systems, or something like that, then the situation is simple, and we can even draw some distribution and develop classical intuition, saying, okay, this is that state, this is classical state, this is squeeze state, or something else. In general, this is not the case. Although the approximation I will be talking about can be applied into any situation because of this analytic approximation. And besides of having this map, we have to equip our theory with a method of calculating of average values. Usually, and there's a reason for this, the people use the so-called Wigner mapping, which is characterized that the average value is computed as a convolution of two Wigner symbols of the density metric of the state and the operator we want to describe. This is so-called dual, self-dual mapping. There are many other mappings. Not all of them are quite appropriate in this case. So, what is the convenience? And what consists the convenience of using the semi-classical method? It results that the equations of motion, exact equations of motion in the phase space, can be naturally expanded precisely over this small parameter, the inverse effective size of a system. It appears immediately. H bar is not a good parameter. The good parameter could be the inverse number of average inverse number of excitations, spin size, energy, or something else, but not H bar. H bar is not a good parameter. And it results, so we can apparently solve this equation and compute the evolution of the Wigner function. It is impossible. It is never possible, let's say. It is never possible because these equations contain high order derivatives. So solve it exactly, basically impossible. What people do? The following: since there is a natural expansion, and this parameter epsilon appears naturally, appears as it is without doing any work, we can cut the higher orders and keep only the zero approximation. And it results that the zero approximation, the equation of motion is just the Liouvillean equation, which can be obviously solved in terms of classical trajectories. Then appears this semi-classical approximation. We just think, without any good reason, that our Wigner function moves along classical trajectories. I will later explain what does it mean in some particular cases. I will focus here in this talk on spin-like systems. Spin-like system, basically, there's not only spin system, many systems which has some internal symmetry or which preserves the number of excitation, for instance, they belong to this class. And if we have a single spin, in other words, that we work in a single irreducible representation of a CO2 group, then the corresponding classical phase space is just a two-dimensional sphere. Perfect. We can draw pictures, say, oh, look at this. This is a very nice picture for the cat-like state. This is squeeze state, coherent state. Very nice. What else? What else? A natural parameter, which is the inverse size of the spin, appears here. How it appears? It appears precisely in this approximation when we cut all the high order terms and keep only the zero order solution. So we believe that our initial distribution moves along classical trajectories. What does it mean? This means something very simple. We can see it. So if our evolution is linear, what we have only solid rotation of the distribution of the sphere. But if the Hamiltonian is not linear, these classical trajectories actually lead to a deformation of the initial distribution. So instead of having coherent state, we have something else. And we say, this looks like a squeezing. This looks like a squeeze state. Maybe we can use this approximation and compute something. It is not completely true. Okay, let's first see these nice pictures, which was done not by me. So this is the simplest exactly solvable Hamiltonians describing so-called Kerr-like interaction. So the initial spin is coherent state, and then this is the evolution. The size is not very large here. I think something like 10 maybe. So this is how the initial state evolves, how it deforms, and see, well, for short times it looks quite good, but for longer times, the exact evolution leads, in this case, to formation so-called Schrödinger curves. So distributions splits into different pieces and actually generate this interference picture. Semiclassical, in the semiclassical case, of course, we cannot describe the splitting of the initial distribution. Why? Because what does it mean, this approximation? We get the distribution, some point, it just move it along some trajectory. So we cannot split the distribution in pieces. So where I told you this approximation is not good, actually it is broken from the beginning, because it results that if we have this Wigner function which evolves along classical trajectory and reconstruct the corresponding density operator, because recall the map is one-to-one. If we have state, we have a Wigner function. If we have Wigner function, we have a state. So we reconstruct the state. It is not a state. It is an object which it is not even positive definite from the beginning. And at some moment, actually at this time scale, which is about 1 over spin size, dimension, 1 over dimension, it basically breaks. And yes. No. Here spin is something like 10. Okay, it is just, sorry, it's just language. Angular moment. But I'm talking about angular moment. When I say spin, think in angular moment. So it is a large angular moment. Well, strictly speaking, if we talk about the integer spin, it is a sphere. If the spin is not, yes, it is a sphere. The phase space is a sphere. The phase space corresponding to the angular moment is a sphere. The phase space is a sphere. Yeah. It is a projective space, but for integer sphere, it is isomorphic to the sphere. Yes. Okay, we can discuss it later. Well, it is isomorphic to the sphere in this case. It is absolutely isomorphic. In case of integer sphere, in integer spins, it is absolutely isomorphic to the sphere. So it is one-to-one correspondence. Case of integer, yes. Okay, we can discuss it later. So this object is not positive definite. So it starts to be negatively, quite well negatively defined for quite short time. Even more, if we write the evolution equation for this object, reconstruct from the Wigner function, evolving along classical trajectories, this is we get this Lindblad type evolution equation where the effective Hamiltonian is not the initial Hamiltonian, and there are half positive and half negative Lindblad-like terms, which is quite strange. So, however, if we apply this approximation for computing something, it results that may help. Actually, this approximation behaves quite differently if we start with stable or unstable situation. Stable means that we put our, it is easy to understand on the level of pictures. If we put our state in the minimum of potential, then the dynamic is stable. So it's kind of oscillation. Maybe non-linear, but oscillation. But if we put the distribution here, to the point corresponding to the classical separatrice, the dynamic is unstable. So it is in a quantum level rapidly splits in pieces. And one can prove that in case of stable dynamic, the time where semiclassical approximation more or less works is quite short, is 1 over square root of the spin size. And this is actually one of the problems which is not usually discussed in papers and books. When I apply a kind of approximation, what is the applicability of such approximation? So what we can really use with the approximation? So it results the semiclassical time where the approximation more or less work is short, and it is not good. So we cannot describe any moment. We can describe only some low order moments of spin variables. in case of stable dynamics. In case of unstable situation is even much worse. So, for instance, why this approximation still works and works much better when in comparison with substitution in Heisenberg equations operators by function, because many effects happens in times even shorter than this time. So the correlation process in quantum system, in large quantum system, are very fast. For instance, the spin squeezing, the best spin squeezing happens in this time. So it is short than this, and we can describe in this way. Well, when we talk about, when we see in the book or in papers, truncated Wigner approximation, usually what does it mean? This means the calculation of this integral. We have the initial distribution and integrated with the distribution corresponding to the observable, which evolves along the classical trajectory. And here is exact simulation. So we can see in case of stable evolution, squeezing, which is the best squeezing, is around here, is well described. In case of unstable, even this squeezing, okay, we have something, but we don't know if it is good, it is bad. Just showing that the dynamics of stable and unstable system is different, and we should be very careful. Well, so the question is, if we think about evolving initial quantum distribution along classical trajectories, is it good or it is bad? It is good for a short time. But if we want to go further, we need something else. What else, for instance? And there were several intentions to improve this approximation. And the following idea came up. Actually, from the quantum point of view, we cannot distinguish trajectories which arise very close from the same Planck cell. They're indistinguishable from quantum point of view. So we can distinguish trajectories which start from different Planck cells. So let's divide our phase space, into Planck cells, which in different cases would be different topologies, would have different meaning, and evolve in this way. So basically the approximation is the trivial discretization. So we have the state and different Planck cells evolve along different classical trajectories. It does not help, unfortunately. It does not help. Basically, the time range is practically the same. So what to do? So we want to, it would be nice, because the idea itself of discretizing the phase space is very nice. So if we want to compute the average value by discretizing phase space, the question is, what would be a nice set of sampling point? Or is it possible to find sampling point which would lead to a long time evolution? Maybe not describe, but at least emulate. So it looks like quantum evolution, maybe at least for some observables, not in general, not for the Wigner function, but for some observables. So it is a trick how to fool the nature, basically. And it results, there are several possibilities of such discretization. I have here, I've planned to discuss 3 of those, but if the time is up, I'm just cut at any moment. So one of those discretization is related to what Luis explained yesterday, to the idea of Majorana representation. So basically, according to this representation, we can put in correspondence to any state zeros of some polynomial, which is basically overlap between the state and the, in this case, spin coherent state. The same as zeros of the zeros of the Q function. For instance, to a single coherent state corresponds just 1 point. Importantly, if the coherent state, if the block vector which goes to the coherent state is here, the Majorana point is just on the other side of the sphere. In other words, these Majorana points are never in the distribution. They are always somewhere around, never there, never on the distribution. So let's think what happens with this single Majorana point corresponding to the coherent state, for instance. So we have initial point here. This is Majorana point corresponding to the coherent state. And what happens in case of quantum dynamics? And it results that the situation is very simple if the dynamic is linear. This point just moves, rotates. But if dynamic is non-linear, it results that this single point splits and splits very rapidly. In this case, in two S points, like here. So have single, boom, they split. So basically what we have is if the initial moment we have just a single point, it's at some moment we have two S Majorana points, which originated from this single point. And then we do the following. We have a single Majorana point which was here. Let's consider coherent state. Which is a coherent state? Single Majorana point which is here, and then apply quantum dynamics. During the quantum dynamics, a single point splits. Actually, this is exact. This is not picture. This is just exact calculation. This single point splits in many, and what we do is project out these many points into the distribution, and try to sample this distribution by the point, by this projected Majorana point. So we have something like this, and let's call it sampled Wigner function at some tau, at some point, at some tau moment. Of course, it is not clear what is the best time. Is it possible to do this or no? It's not quite clear. Let's try. So we try to maximize the fidelity, so overlap between the initial distribution and this sampled point, and see what is going on. It's possible to do it, is not. It looks from the first sight as a crazy numerical work, because find even numerical evolution of Majorana points in case of large, say, I don't know, 1000, dimension 1000, when dynamics is really important, because if 10,000 we can exactly diagonalize the Hamiltonian. There's no worries. 10,000 we cannot. However, it results that this is the equation for Majorana point. At short time, this equation can be solved. Это не каждый дурак может сделать. This equation can be solved analytically, and this is the form of equation where coefficients are some zeros of Hermite polynomial. Does not matter. It can be solved, and if it can be solved, then this maximization, the maximization of the fidelity of the overlap between exact and sampled, can be in many cases done analytically. If not, it is a very easy numerical work. I mean, the computer do it in a few seconds. Well, example, the same Kerr model, initial coherent state. This is the distribution of projected Majorana points. The points inside of this circle are needed to sample the initial distribution. Actually, these are exact equations, does not matter. So if we use this approximation and then move every point of this evolved Majorana, every evolved Majorana points along classical trajectory, then kind of miracle. We describe evolution for long time. Actually, we don't see any limit for this. This is trivial case. Okay, this is not, doesn't matter. Stable and not stable dynamics. One suspect that in case of unstable dynamics, the situation is different, because actually when we talk about, again, when we think about semiclassic, maybe you have read it, the people always think about something compact. The state should be compact, semiclassical, not extended, not fluctuation very much. So this is not completely true. This method, for instance, works, and here for this Lipkin model, where unstable evolution is present, sometimes the people call it dynamic phase transition, second order quantum phase transition. So the evolution again is quite well described. Just to convince you that it works. And here, oops, sorry. And here actually the graph of fidelity, this numeric fidelity. So you see the time where the fidelity takes basically unity value is very short, so approximation works. Interestingly, maybe it is seen, maybe it is not. It can be applied not only to the semi-classical distribution, but to, for instance, to a quite non-semi-classical distribution. For instance, decay state. Basically, this is the angular momentum state with zero projection, which Wigner function is a belt around here. And these actually are the projected Majorana points. So works. So what changes is the number of points we should take in order to sample well the initial distribution. Well, I think this is it. This is the first method. Any question? I'm going too fast, and it is difficult to understand. Please. Yes. Yes. Actually, the standard semi-classical description is this. So we evolve the distribution corresponding to the observables along classical trajectory and overlap it with the initial distribution of the state. And this is how we compute average value. So strictly speaking, the approximation has two pieces. One is evolution and another one calculation of this overlapping integral. You can see it here. You can see this is exact evolution and this is semi-classical evolution. This semi-classical evolution sometimes describes few oscillations, maybe 1, 2, 3, depends of what moment do we want to describe. It does not work. It does not. It depends on the state. We can talk it later. We can talk later. Yes, because okay. Now let me go to the next item. What happens in case of when the spin is not fixed? What does mean spin not fixed? Spin not fixed means the state belongs not to a single irreducible representation, to some of them, or maybe even infinite number of them. What happened in this case? In this case, by the way, there is no classical phase space. We cannot put in corresponding classical phase space. For instance, in case of rigid rotor, which is basically this kind of state, have infinite number of subspaces involved. There is no classical phase, exact classical phase space. If we want to keep some of the features of the spin approach, which just see, it results that an operator can be mapped into a set of operators which live on the three-dimensional sphere, not two-dimensional sphere, three-dimensional sphere. This phi and theta are on two-dimensional sphere, this psi, three-dimensional sphere, and depends on one new index j. In this case, all the map can be constructed. This is SU2 invariant and so on. And there is a formula how we compute average value of basically of anything in case of exact map. Moreover, for instance, in this case, one can find also the so-called star product, so put in correspondence to any product anything, and write evolution equations similar to Moyle equations. And some of those equations are quite nice, look quite nice. For instance, for a couple spin, we have a very simple equation. And it results that in this kind of map, what one can do is take continuous limit of this index j. So again, we start with state which lives in many subspaces. We project it out into distributions which labeled with a discrete index. And then we take a continuous limit. We take a continuous limit. And we have a function of 4 variables. Actually, one can show that there are marginal distributions, so there are projections of this guy into the sphere or into the cylinder. But this is not that important. It results that since we have the exact evolution equation, when we take continuous limit, we can cut it at first order on this parameter j, which actually corresponds physically to the average angular moment of our system. And it results that this evolution equation, it is a Liouville equation, but not on the sphere. It is on the tangent bundle to the sphere. So it is on 4-dimensional manifold. But it is still classical evolution on 4-dimensional manifold. This means that we can solve this equation and we have this semi-classical approximation. We have this semi-classical approximation. The semi-classical approximation means we have trajectories, classical trajectories on 4-dimensional subspace. In other words, interesting result that a variable spin system has an approximate phase space, which is a tangent bound to the sphere. Okay, and in principle, we can construct this naive semi-classical approximation, integration as we agreed. It does not work. It works only for short times. So something else is needed. I mean, it works. Many people actually do this. For instance, I don't know what name of the previous speaker. He cited a guy Polkovnikov. He has reviews about semi-classical approximations. When this is it. But if you took a look, you see that the time is very, very, very short in this case. Well, we need something else. And the idea, the stupid idea is kind of easy. Let's now go back and discretize the parameter j. So we start with discrete j. We go to continuous limit. In the continuous limits, we have classical evolution equation. And now let's try to discretize this index j. But the question, how to do this? But it results, again, since we have this star product, maybe somebody knows, we can develop the procedure which is called deformation quantization and quantize this index j. So basically find its spectral decomposition. After doing a lot of math, algebra, basically, we arrive to the modified, discretized semi-classical approximation. So instead of integration, we have sum, we have evolution along classical trajectories, but something else happens here. We need to be very careful what is the initial distribution. For instance, parity appears here and so on. And it results that this work very good. For instance, this is rigid rotor, Hamiltonian, very complicated to do this numerically. If the rotor is highly excited, say the quantum number is, I don't know, 1,000, calculations basically impossible. So what we can see that it describes evolution very well. So this is the truncated Wigner approximation, semi-classical approximation. See, we see only the first collapse, but in this discretization case, we describe very well the second collapse, and actually all the other collapse later on we have some dephasing problem and so on. The same happens in this case of two coupled spins. It is much easier system, but again, the description of semi-classical only first collapse. This discretize, we can describe many collapses. But again, there's stuff here. There are two kinds of evolution. There's fast evolution and slow evolution. So what is possible to describe is fast evolution, but slow evolution, it fails also. Something else is needed. Well, good. Can we do something else? yes, we can do something even more stupid, actually. The idea is the following. We want to use classical information in order to catch some of quantum dynamics. We can use classical trajectories, but instead what we can do is to use classical spectrum. What is classical spectrum? We have Hamiltonian, find it classical correspondence. Wigner function is the best among all the possibilities. And we proceed with a so-called semi-classical quantization. What is this? We find the classical period of motion, get the action, and apply, for instance, the Bohr-Sommerfeld quantization in case when the system is effectively one-dimensional, which is spin system. We can do this. So from here, we get the semi-classical spectrum. Having the semi-classical spectrum and having the exact Hamiltonian, what we can do is reconstruct eigenstates of the Hamiltonian corresponding to the given semi-classical, to the given spectrum. And instead of exact spectrum, we substitute semi-classical spectrum. And actually, this inversion is very simple. When we start to do this, we actually developed this approach. It's actually a very simple approach because it's just a vector constituted by semi-classical eigenstates, and we apply some metrics constructed out of Hamiltonian. But later on, we found even the standard get-vec algorithm, which does this in a few minutes. And now, the crucial point is to recover the idea of unitarity evolution. Because as we agreed in the previous consideration, the evolution was not unitary. Actually, this evolved Wigner function does not correspond to any good operator, does not correspond to a state. So that what we do, we have semi-classical spectrum. We have semi-classical states reconstructed from the spectrum, and we construct the semi-classical evolution operator, just like this. And this is it. And this is it. And if you try to apply it to any case, so just perfect correspondence. This is kind of trivial case in a sense. Lipkin model, stable and unstable regimes. Let me show how it can be applied. In case, actually, the case of single spin, like here, the system is effectively one-dimensional because we are in subspace of fixed energy. We fix the energy value of Hamiltonian over the initial states. So the system is, we can use the Hamiltonian as an integral of motion. In this case, the system is not, when you have two coupled spin, the system is not one-dimensional anymore. So different kind of Weyl quantization can be used. But actually, this Weyl quantization works quite well. This approach, for instance, allows to describe spin-like systems not that simple. For instance, the famous decay model. We know that there are two analytically solvable limits. When have a lot of atoms, a few photons, and have a lot of photons and few atoms. Then it can be solved analytically. However, there is a case when the maximally unstable case, all the atoms are excited and zero photons in the field. This is very complicated situation to develop any perturbation theory. However, this method works pretty well. It results that this Hamiltonian can be exactly mapped to this effective Hamiltonian where only spin variables are involved. This is exact mapping, one-to-one. We can find the classical Hamiltonian and equal it to the energy. I'll just show how this method works in this particular case. The initial state, all atoms excited, corresponds to the average energy 0. Average energy. We quite easily that trajectory, find the classical period, and it results the classical period has this form. And according to the standard quantization scheme, this gives us just energy density. And this is it. Then quantizing and applying the method I've just described you, we have perfect description of anything, of very complicated situation. And here, for instance, here the action, the adiabatic invariant, is a function of energy. And we see, so what interesting, that in this approach, we can see this so-called phase transition, which is not phase transition, just instability on the quantum level. Here have change of derivative, precisely. And here, this is the sign of, say, very dense level spectrum, which corresponds sometimes in the thermodynamic limit leads to this phase transition. The difference of energy is a function of adiabatic invariant. You see that this is when the states becomes very, very dense. So method, very trivial method, where the idea of unitarity is applied, works basically better than anything else without doing any other approximation. Of course, it works not for all states. Not for all states. There are several restrictions here. However, it is very easy, very, very easy to use in applications. All the other methods can be used in different situations, and all of those are numerically very easy to implement. So there's not something you have to really struggle with. Okay, this is it. And the main message is we cannot deal only with classical dynamics. We need something else. And this something else could be, among many other things, could be discretization or of some parameter. And this parameter we choose, and it depends on the physical system we work with. This is it. Thank you very much.